Hello, everyone. Today, we're going to talk about the non-level payment annuities and perpetuities. We're going to talk about two types of progressions. One is a geometric progression. The other one is arithmetic progression. For non-special type of progression, we're going to just use the basic principle of discounting back to the time zero or accumulate to time n, using just using ad hoc method. But for these two types of progression, there are formulas that we can use. They are a little bit complicated, but let's study some of them. Okay. The first one is a geometric progression. So suppose that an annuity has payments with each payment equal to 1 plus G times its predecessor. Let I be the effective rate for each time period, and say assume that annuity is an annuity immediate, lasting for n payments. The initial payment is P. And assuming AI not equal to G for the moment, and we're trying to figure out the formula of the present value. I think it's just mainly present value. All right. Future value can be also obtained as to but normally we calculate the present value. Let me draw the timeline to see the situation clearer. 0, 1, and 2, and time n. Okay. And the end of the first time period, we have a payment P, and then the second one, P times 1 plus G. And finally, we have a P times 1 plus G to the n minus 1. You see, you have a 1 plus G to the 0 here, 1 plus G to the 1, but you have time 2, so it's 1 less than the time. So the power is 1 less than the time. Okay. So now we try to figure out the present value here. Basically, you discount everything back to time 0. So I have P times V, and then you have a P times 1 plus G times V squared. By the way, V is the discount factor, which equals 1 over 1 plus I. You have a common factor of PV and moved it out, multiply by 1 plus G times V plus dot 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 plus 1 plus G to the n minus 1 times V to the n minus 1. Okay. And then we have geometric sequence, the sum of the geometric sequence here. And the formula is like this: 1 plus R plus dot 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 plus R to the n minus 1. The formula is 1 minus R to the n divided by 1 minus R. You have a 1 more than that, okay? So we have PV times 1 minus 1 plus G over 1 plus I to the n divided by 1 minus 1 plus G over 1 plus I. Okay. And then V equals 1 plus I, 1 over 1 plus I. So this is 1 over 1 plus I. So you're gonna multiply the bottom by 1 plus I. So you have 1 plus I minus 1 plus G. So you have I minus G. And the numerator is 1 minus parenthesis 1 plus G over 1 plus I to the n. Okay, so that's the formula. When I equals G, the denominator is 0. So the formula doesn't work, but you look at uh, here. Uh, 1 plus g times or divide by 1 plus I would be just 1. Okay, I equals g just 1. So it's essentially you have n terms, so you have n times p then times v. So essentially it's n times p times v. Okay, so these are the formulas. Uh, the next slide has a lot of formulas for arithmetic progression. What means is this? So let me draw the timeline to just to make the situation a bit clearer. So time 0, time 1, time 2, and time n. So you have P here. So each time period you're gonna pay P, but then uh, just starting from the second one, you add Q there. So you have 3, here's P plus 2Q, and then finally you have P plus N minus 1 times Q. Okay. So in order to find the present value, you discount back to time 0. If you want to find the future value, you accumulate to time n. The mathematics is a little bit involving because we have a q, 2q, n minus q. It's not very straightforward. We need to do something, but I guess I'm not going to do that. So I will just rewrite these formulas, just to consider it as a formula, as a notation and formula. Okay, I means increasing. Okay, and P is the original payment consistent throughout the time, and Q is the increasing amount. And the S is the accumulated value, that's the future value. And sub N is the total number of time periods. Then this I is the interest rate. And the formula is P times S N angle I. And then you have Q over I times S N angle I minus N. Okay, so that's the formula for the future value. Uh, the the present value is we have I, P, Q, and A here, and N angle I that equals it's a present value. Okay, it's P times A sub N angle I plus Q over I times A sub N angle I minus N times V to the N. Again, V to the N is the discount factor. It's 1 over 1 plus I. We have another two formulas with two dots, the annuity due. And I guess I'm gonna just skip that one. For IS, which means when P equals Q equals 1, and we have IS, that's the future value, and angle I, just, P equals 1, so you have A sub n angle I plus uh, 1 over I. I think there's another simpler formula, which is, hold on a second, this is S, so sorry, this is S, we're talking about S. S n angle I plus 1 over I, so it's S n angle I minus n over I. Okay, so And I think you can put these two terms together, but I think I'm gonna just skip that. Here actually we have Sn plus 1 angle I minus n plus 1 and then divided by I. Okay. If you put them together, you plus right. So if you put them together, you would have I on the bottom. You have I time 1 plus I times and plus 1 times. So you have I 1 plus I times S n angle I minus n. Okay. Uh, this is annuity due. This is actually annuity due as two dots and angle I minus n. Okay. But then you can also consider it as a Sn plus 1 angle I minus 1 and then minus n. So these two are the same, okay? These two are the same. So minus 1 minus n, putting together you have n plus 1. Anyway, these are this is the formula for increasing arithmetic progression with p equal q equal I. And we're talking about the future value. The present value, IA sub n angle I, that will be equal to due n angle I and then minus n times v to the n over I. Okay. This is 1. This is also 1. And you put them together, you would get A two dots that the annuity due. And DA is this thing. You start with n, and then you have negative ones. Next one is n minus 1, n minus 2, and you have the timeline. So it's 0. You have 1, 2, and then towards the end, n. What do I have? N plus 1, n plus 1. You have 1 here. Okay. It's decreasing, but with 1 and 1 p equal 1, q equal 1. So dA, the notation is the present value, okay, equals n minus a sub n angle I over I. Okay, that's the formula for the arithmetic progression with p equal z 1, q equal 1, q equal negative 1 actually. Sorry, q is negative 1. P is n. Sorry, this is not p q equal 1. This is for when p equals n and q equals negative 1. All right, starting from n and get back to 1. All right. So the graph is right. What I said was not correct. It's not p equal 1, q equal 1. It's not. All right, let's look at some examples. The calculation is a bit involving as well, so I'm not going to give detailed calculations. All right, so the first one, an annuity provides for 10 annual payments. The first payment a year, hence being $2,600. The payment increase in such a way that each payment is 3% greater than the previous one. The annual factor rate is 4%. Find the present value of this annuity. And so let's draw the timeline. If you have a very clear mind, then it's probably not necessary. How many payments? 10 payments. The first one is $2,600. and then 2,600 times 1.03, and then 2,600 times 1.03 to the ninth. Okay. Sometimes I directly work on the cash flow and using the sum of the geometric progression. But here it's kind of standard, very standard setting. So we can use the formula, the present value equals Q, which is 2,600 times P. Actually, we use P for this formula, but anyway, it's 2,600 100 times 1 minus 1 plus G. G is what? G is 0.03. And then the interest rate 0.04 to the n, you have 10 here, then divided by I minus G, okay, and it's to $23,945.54. Okay, and that's this problem. Next one, it's in perpetuity. Now, perpetuity immediate provides annual payments. The first payment of $13,000 is 1 year from now. Each subsequent payment is 3.5% more than the one preceding it. The annual effective rate of interest is I equaling 6%. Find the present value of this perpetuity. So the perpetuity is the present value of the perpetuity. Let's work with the formula when we have n periods and then let n go to infinity. So the formula is P times 1 minus 1 plus G over 1 plus I to the n over I minus G. Now, when G is smaller than I, so I have 1 plus G over 1 plus I is smaller than 1, and you raise the power by n, when n goes to infinity, this term will disappear, it goes to 0. This term goes to 0 when n goes to infinity, okay? So if we have infinity here, then it disappears. So the present value of the perpetuity would be simply P times, P divided by actually. So P divided by I minus G. So here we have a 13,000 over 0.6 minus 0.06, 0.035, and we get $52,000. Yeah, that's this problem. All right, let's look at another example. Find the present value at time 0 of annuity immediate such that the payments start at time 1. Actually start at $1, the one something one, okay, not may not be dollar, but just start at 1. Each payment thereafter increases by 1 unit until reaching 10. And they remain at the level until 25 payments in total are made.我在录课，你稍微等一下，我马上就好了啊。All right. let's see, I want it to be like this. Okay. Let's draw the timeline, make it longer because we have two types of settings, 0, 1, 2, until 10. And then starting from 11 to 25, we have a level payment. So 1, uh, increase by 1, so you have 2, and you have 10, then you have 10, 10. Okay. So the first part of annuity actually has a base payment $1 and then increase by $1. And so actually we have IAPQ equal 1. So the present value here, we're going to use this notation IA, and you have 10 payments and 0.04. Okay. This value is for this part. Okay. And then for the leveling payment, this part, and the value here at this time it would be 10 times A. Totally we have a 15 payments here. Okay, 15 payments. All right, 15 angle 0.04. And then you need to discount back to time 0. Discount back to time 0. And I'm not sure this notation is this arrow is good, but probably I just do this. Okay. It will be 10 times A sub 15 angle 0.04 times 1.04 to the negative 10. Okay. And then you add them up. Add them up. On IAG, that one is a little bit complicated. So let me write down the formula, and I think I'm gonna skip calculate. Maybe yeah, okay, I have the answer. So it's A sub 10, two dots actually, 0.04 minus 10 times 1.04 to the negative 10 divided by 0.04. And that equals 117.10. Okay. Hold on a second. Is that the total? Probably. Actually, that's not correct. So I'm gonna erase that one. The summation, the total, so the answer is 117.10. And that one, actually, I don't have the answer. So this one, I can write this one is A sub 10 and 0.04 times 1.04. Okay, it's the present the annuity due, the present value of annuity due. It's the annuity immediate times 1.04. Okay, so I'm going to skip the detailed calculations. All right. Next example. Find the present value of a 15-year decreasing annuity immediate, paying $150,000 at the first year and decreasing by $10,000 each year thereafter. The effective annual rate is 4.5%. Okay, so time 0, time 1, time 2. So at the beginning, I have a 150,000. then 140,000 and 15 year. So I have 10,000. Okay. The way I look at it is that 15 plus 1 is 16, 14 plus 2 is 16, so 1 plus 15 is also 16. So the last payment is not 0, it's 10,000. We're looking for the present value, okay, present value. So here P equals 150,000, and then Q is actually negative 10,000, and N equals 15. So the formula would be IPQ A sub N angle I. Okay, so that would be P times A sub N angle I plus Q over I times A sub N angle I minus N times V to the N. P, just plug in these numbers, 150,000 times A sub N, which is 15, angle I, 0.045, minus Q is 10,000 over I, 0.045, and I have A sub 15 angle 0.045 minus N, 10 times V, 1 over 1.045 to the 15, and then another parenthesis. Okay, so that value, I'm gonna just look at the answer. Okay, okay, that's the answer. One more question, one more example. And an investor is considering the purchase of 500 ordinary shares in the company. This company pays dividends at the end of each year. The next payment is 1 year from now, and it is $3 per share, 500 shares, right? So actually it's $1,500. The investor believes that each subsequent payment per share will increase by $1 each year forever. Calculate the present value of this dividend stream at a rate of interest of 6.5% per annum effective. So annual effective rate 6.5%. So let's draw this. Well, do we need to draw it? It's perpetuity. So probably we don't need to draw it. P equals $3. Okay, and then Q is $1. All right. So for each one, we have well, it's a perpetuity, so it's just I, and we're looking for the present value. So P, Q, A, we'll have infinity I 0.0. Let's put I for the moment. Yeah. The formula, so we have P times A sub infinity angle I plus Q over I times A sub infinity angle I. And there's a term n times v to the n that equals n over 1 plus I to the n. When n goes to infinity, this goes to 0. The denominator is exponential, has exponential growth, and the numerator is just a polynomial, so it goes to 0. All right, so for this problem, it's 3 over I. I is 0.065, 0.065. And then Q, this is also 1 over I. So you have a Q, which is $1 over 0.065 squared. This is 1 over I. Okay, so that's Q over I squared. I have that. That's for per share. And we have 500 shares. So we're going to multiply the whole number by 500. So the answer will be 500 times 3 over 0.065 plus 1 over 0.065 squared. All right, the answer is 141,000 for 20.12. This is a simplified version of calculating the stock price. In reality, that's actually how we do. You just need to predict the dividends and then use the interest rate to discount back to time 0, which is now, and that is the stock price. Okay. All right. Uh, do I have another question? I think there's another problem. Yes, let's work on that. John deposits $6,000 in the end of each year with interest rate 6%. However, the interest earned can only be reinvested in an account to earn 4%. So it doesn't have 6%. After 20 years, find accumulated value. So here actually there are two accounts. So I'm going to draw a timeline as well, but the situation, there are two accounts. So the situation is not that bad. So you have a 0, 1, 2, and the 0, 1, 2, maybe 3. And then we have a 20 years. Okay. So this is account 1, and this is account 2. In account 1, John deposits $6,000 in the end of each year. For this account, the interest is actually not included because interest is taken out and is reinvested in another account, which earns 4%. So for account number 1, the accumulated value will be just 6,000 times 20. That's $120,000. Now for the second account, it's a little bit more interesting. So in the end of the first year, nothing happens because there's no interest. And in the end of the second year, I have, John would have $6,000 times 0.06, which is the interest he earned from the first account. But it will be invested in the second account. So it's 360. And then the next year, 360 doesn't disappear, right? And also this interest earned from this amount. So another 360. So 360 plus 360. Or maybe 360 times 2. And then finally, in the end of the 20th year, 360 times 19. Okay. 2 is 1 less than 3, and you have 1 is 1 less than 2, so 19. 1 less than 20 is 19. Okay. So here we have a arithmetic progression with P equals Q equals 360. Okay. And then we're looking for accumulated value. So I'm going to use I sub 360, 360, and S. Uh, the number of payments here is actually 19, not 20, because here you have zero, okay, nothing here. So it's actually 19. And angle 0.04, the interest rate 0.04. And we calculate it out. It's 88,002.36. Okay, and you add them up, you will get an answer. I think it will be given by this $208,000, $208,002.36. So I think that's about this section. Actually, there are three sections. The first section I didn't give examples, but you just use the ad hoc method using discounting or discount factor, or if you uh, accumulating uh, to some time. Okay, so just use normal principle. Uh, but these following two sections have some special type of progression, and we have some formulas to use. Okay, and that's for today. I'll see you later. Bye bye.